Now that we've completed lab number 3 and you have some experience with activating a nerve with many different types of stimuli, let's focus on what was described on page 30 of your lab manual and how it corresponds to figure 7.14 in your textbook. If you need to grab these materials, go ahead and do so now. You should be able to identify 3 different types of signaling so far: a graded potential in the depolarization direction versus a graded potential in the hyperpolarization direction, and how those are different from an action potential. We'll review these now. On more than a few of your papers I was grading yesterday, the lab reports all had the same mistakes being made on the 3 graphs you all turned in on page 35 of your lab manual. Hopefully you will go back today and make these corrections after listening to this lecture. Okay, when comparing graded potentials, we must first locate the threshold, highlighted here in red. The graded depolarization is a result of some stimulus being applied to the neuron, which caused the membrane to depolarize slightly towards the positive direction without meeting threshold. The same is true in the hyperpolarization example in figure B. Instead of going in the positive direction, the stimulus causes the membrane to become more negative than normal, which is even further from the red threshold line. The threshold level must be respected at all times when evaluating the neuron's response to any stimulus. Threshold is usually a membrane depolarization event of about 15 to 20 millivolts. So that'll put you at about minus 50 to minus 55. This is caused by the total amount of ions flowing through the membrane. Weak or subthreshold level stimuli are not converted into action potentials, and that's why they look like a little bump in the road here. They quickly go back to the resting membrane level, so there's very little disruption to the neuron overall. Strong stimuli that make the neuron reach threshold are what get converted into action potentials. Action potentials have an all or none behavior. They either happen completely or not at all. Action potentials are only generated by a neuron or a muscle. An action potential can be defined as an all or none electrical event because it has this massive electrical change that happens very quickly, within milliseconds. And action potentials can be described as a brief reversal of membrane potential with a total amplitude of 100 millivolts. They do not decrease in strength or peak height over distance. They are the primary means of neural communication in the brain and to the body. And an action potential traveling along the axon is what we call a nerve impulse. There are 3 main phases of an action potential. If you take into consideration the resting membrane potential, which is constantly maintained by the sodium-potassium pumps, which are always on, the cell is constantly using ATP energy to kick out sodium and pump in potassium, then we understand how the cell maintains a flat line, seen here numbered as number 1, before and after the peak, resting membrane potential. So on the computer screen, when there's no stimulus being applied, you have a flat line, labeled as number 1 here on this graph. The flat line is at minus 70 millivolts, constant, until some disturbance or stimulus occurs. The different phases of the action potential are highlighted here. So we can start at number 1, and we can see that the resting state occurs before and after the peak of the action potential. The cell will rest before and after the action potential. Phase 2 is the rising phase, where the membrane becomes permeable to sodium, and sodium rushes into the neuron, causing depolarization to threshold, and then way beyond that to a plus 30 millivolt peak at the top. And then we see a rapid decrease shown in phase 3, where the cell recovers back towards resting. In phase 3, sodium is shut down and only potassium is being lost. The loss of a positive ion helps return the cell to a negative resting potential. Phase 4 is a temporary hyperpolarization phase where the potassium channels remain in the open position longer than what is needed for recovery, and the measurement shows that the cell is more negative than normal for only a brief period of time. Every action potential has all three of these phases. You will need to be able to not only identify the three different graphs I've just described for you, but also be able to draw them on your own correctly. That means place the resting membrane potential and the threshold level on your set of axes first, and then draw the appropriate neuron response, whether it's graded or a full-on action potential. You need to be able to draw these on your own. So the action potential moves away from the source of the stimulus and travels the distance of the axon. In this figure, we can associate the peak of the action potential with the opening of voltage-operated sodium channels. And where they are closed corresponds to the return of the resting potential. Also note where sodium channels are closing, potassium gates are open and create a current or cation flow. Ions in the ECF move toward the area of greatest negative charge, and current is created that depolarizes the adjacent membrane in a forward direction. The impulse propagates away from its point of origin. Remember the role of the sodium-potassium ATPase pump? It maintains resting membrane potential and helps with the repolarization phase after an action potential peak. Active transport works to restore the resting ionic conditions of the neuron, so it works to restore the resting electrical conditions inside the neuron. Neurons depend on the sodium-potassium pump to respond to stimuli and transmit electrical impulses. As we transition today into chapters 8 and 9, we start to see how these action potentials create patterns that are sent and received by the central nervous system. One key feature of our action potential is that they're all alike. They function as all or none, which really means the initial depolarization event either reaches threshold or it doesn't. So if all action potential signals are the same, plus 30 peak height, and they always meet threshold, then how does the brain interpret all these signals? It has to do that with frequency. That means how fast are they coming along the axon? Strong stimuli can generate an action potential more often or more frequently than a weaker stimulus. The central nervous system determines stimulus intensity by the frequency of impulse transmission. So the coding patterns can look like this, where we see initially the stimulus, indicated by the red arrow, causes a graded potential. Take your finger and point to the graded potential. It's the one on the left. We're going to read this graph from left to right. Now, we increase the strength of the stimulus, not the axon. So you note the axon is firing an action potential in quick succession, and our action potential peaks look like little lines shooting straight upwards. This is because they are compressed along time. Time is on our x-axis. If the stimulus increases again, we see the action potential peaks get closer and closer together along time. The neuron is firing more frequently, which, with the increased strength of the stimulus, indicated by the red arrows, you increase how fast the action potentials are coming along in time. So the peak heights are always the same. This graph looks like it's had a little flat top haircut. So all the peaks are the same, and the action potentials look like little straight vertical lines, and they're getting closer and closer and closer together as we read this graph from left to right. The stimulus arrows are also getting bigger to tell you that the stimulus is also increased. Okay, so there's an absolute refractory period. Okay, this is another feature that allows for rapid generation of action potentials without the chance of them overlapping in time, which is on our x-axis. If two peaks that are exactly the same arrive at the brain for interpretation, then they would be seen as one peak. We want to avoid any overlap with our peaks, and how we achieve that is with an absolute refractory period. The absolute refractory period is the time between the opening of the sodium activation gates until the closing of the inactivation gates. You can look at these again in figure 717. It's a three-part figure, and it shows you the gating mechanisms that are characteristic for the sodium channels. So what happens is, with absolute refractory periods, we prevent the neuron from generating another action potential, and that's the time zone to the left of the vertical dotted line here on this graph. This also ensures that each action potential is separate from any other action potentials being sent. Absolute refractory also enforces one-way transmission of nerve impulses along the axon. There is also a relative refractory period. That's the interval just following the absolute refractory period, just to the right. So in this time frame, sodium gates are closed, potassium gates are open. Notice you're on the downhill side of the action potential, and repolarization is occurring. This is all on the far right side of the action potential peak. The threshold level at this point is going to be elevated, which means only a very strong stimulus would be able to depolarize the neuron again to fire another action potential. But here, they would not be in danger of overlapping. This is often used to increase the frequency of an action potential. For example, you stubbed your big toe on a curb while walking. Ouch. We'll talk about the perception of pain and reflexes next week.